Hello, my fellow quantum enthusiasts. The goal of today's video is to gain some insight on why quantum phenomena is very difficult to observe in everyday macroscopic objects. For this, we'll use a numerical example, an application of the Heisenberg Uncertainty Principle to study how standard deviations on the measurements in velocity/momentum of a pitch, a baseball pitch, are correlated with the standard deviations on measurements of the location of that baseball. The uncertainty principle has different flavors. Today, we're going to discuss that one relating position with momentum. So, take a wave function, for example, a position wave function that describes the location of your particle. You can think, for example, of solutions to the particle in a box model, which are basically sinusoidal waves. And remember that the square of that wave function is associated with the probability of finding a particle in some region of space. For that case, the type of wave function will give you a rather large spread on the possible measurements for the location. Sometimes we refer to this as basically the particle can be found anywhere. The standard deviation on the measurements then is rather large. If you were to look then at the momentum wave function that corresponds to the same particle, you will see that the spread on the measurements for that momentum is rather small. The standard deviation is relatively small. And actually, I'm putting the link for a video in the description in which we went over this kind of case. We're given a wave function, a position wave function, and we calculated the standard deviation on the position of the particle, the standard deviation on the momentum of that particle, and we effectively confirm that the product between those two is bound by a constant number, higher or equal to h bar over 2, where h bar is Planck's constant divided by 2 pi. So the basic idea behind this equation is that there is an inverse relationship between the spread on the measurements, the standard deviations on the measurements of the locations of your particle, and the standard deviations on the measurements of the momentum in the same direction for that particle. And you can see that in these plots. The largest spread on the position, a rather small spread on the momentum. Now, what happens if you have, for example, a wave function that describes a particle that is more localized in space? Then that will correspond to this kind of wave function, a wave packet of sorts. Compare this first wave function with the wave packet wave function. You can still find some spread on where the location is, but the spread is rather small. You can tell that the particle seems to be more localized. The counterpart, the momentum wave function that will correspond to this particle, will look then like this. The spread on the measurements for that momentum will be rather large. And again, this is just a manifestation of the Heisenberg Uncertainty Principle with that sort of inverse relation between the standard deviations of both, the momentum and the position of the particle. Okay, let's land this with an example of everyday life. For this, we're going to be tracing the fastest baseball pitch in Major League Baseball's history. It turns out that Aroldis Chapman, this gentleman here, holds the record for the fastest pitch that stands at around 105.8 miles per hour. According to the current StatCast system that measures, among different aspects of the game, the baseball speed as it leaves the pitcher's hand. Let's suppose that this system uses photons of some green laser, which have a wavelength of about 535 nanometers. And that is used to trace the baseball's trajectory, the position, if you will. And that goes with a precision of about one wavelength, this wavelength. Now, the question is, how sure are we about the velocity that will be recorded with this system under these conditions? Let's use Heisenberg Uncertainty Principle that should be larger or equal to h bar over 2. Let's use proper substitutions, h bar equals Planck's constant over 2 pi, and then solve for this expression here to calculate the spread on the momentum. And then, since we're saying that these systems can locate the particle with a precision of one wavelength, let's use that one wavelength to substitute my equation. And then we find that the spread on that momentum is roughly in the order of 10 to the minus 28 kilograms meter over second. Now, since what we're interested in is in terms of, well, what about the velocity of the particle? How uncertain are we on the measurements of that velocity? We know that momentum is equal to mass times velocity. Using rule 1.09, which says that a baseball must have a mass somewhere in between 5 and 5.25 ounces, let's take a value around the middle of that range and convert it to kilograms. Do proper substitutions to find what the spread will be, the standard deviation of measurements for the velocity of that particle. We take the standard deviation on the momentum divided by the mass of that baseball, and then we find that this is roughly 6.8 times 10 to the minus 28 meters per second. Okay, so then what we're left with is to compare this spread in the velocity with respect to the velocity itself of Mr. Chapman's pitch, which is 105.8 miles per hour. Then we go from miles per hour to meters per second, and we're using these to calculate the velocity of the record-holding fastest baseball pitch. Compare these two. Roughly around 10 to the minus 28 meters per second versus a whole 47.3 meters per second. you can clearly tell that the velocity at which this baseball traveled during that pitch is way larger than the possible spread in the velocity. Actually, about 29 orders of magnitude. So what does that mean for us? Well, it means that because of this very large difference, the indeterminacy established by the Heisenberg Uncertainty Principle is basically negligible in measurements of the motion of macroscopic objects, such as that of a baseball. And that is why, in principle, we cannot observe, at least easily, quantum phenomena for macroscopic objects. This difference is ginormous, and thus effects really are hard to observe in those cases. In the next example, video example, we're going to work out something similar but for a subatomic particle for which this indeterminacy can be relevant, and why we need quantum mechanics to make better predictions about different properties of such systems. But as it was seen here, in macroscopic cases, that's not necessarily relevant. Okay, I'm finishing this video here, but please let me know if you have any questions and wait for the next video. Have a nice day.